Okay, hi everyone. So today I'm trying a format where I've already written down the notes. So we'll see how that goes. Okay, so today I'll talk about K-center clustering, and I'm hoping this will be a short lecture. So it's a very nice, simple algorithm to solve the K-center clustering, which was invented by Gonzalez in the 80s. Okay, so let's get started. So what's the clustering problem? Everyone must have heard about it. It's widely used in data mining, pattern recognition, and machine learning. Right? It's a very important problem there. Okay, so what really goes on there? So we are given an input. Let's think of them as points and some, for this lecture, just think of them as two-dimensional points. We're given n of them. And then look at the picture on the left. We want to kind of create K clusters. By that we mean we want to pick K points from the input, right, and mark them as centers. So they'll be called the centers of the clusters. So here in the figure, we have picked 4 of them, right? And then every other point will decide which is the closest center to it. And it will assign itself to that center. So the points in blue decided that, okay, this blue center will be closest to them. So they get assigned there. They're a cluster of size 3. The black points are a cluster of size 4, and so on. Right? So in that way, we have created 4 clusters here. Right? So the goal here is we have to pick K centers, which is the set C, and then every point in P will choose its nearest center from C. That's the second bullet I've written here. And so this is some notation we might need going forward. Set C and PI. PI will be the set of points of P for which CI is the nearest center. Okay. So now we can always choose any arbitrary set of K points and do this clustering, right? So the whole goal is we will have some objective function in mind. And the way we pick our centers will be such that we want to minimize that particular objective function, right? So the popular objective functions which are used are typically k-means, k-medians, and tons of variants of it. Like this has been extensively studied in the literature, and there are, I'm sure, hundreds of definitions. So it really depends on the kind of application which is there in your mind. That will decide what kind of objective function you want to use. In today's lecture, we'll focus on K-center clustering. Okay, so before I formally define what K-center clustering is, I'll need some definitions to build up to go till there. Okay, so let's say we have some clustering. We picked a set of K centers as a cluster. So then let's just go to one of the clusters whose center is CI, which is shown in the figure on the left, right? And all the points within that green circle are part of that cluster, right? So now the black point on the circumference is the farthest point from CI, right? So we'll define that to be the bottleneck distance of CI. That means that is the farthest point which belongs to the cluster of CI and is farthest from it. Okay, and we'll denote that by delta of CI. Okay, and that's what I've defined here, distance of the farthest point of PI from CI. Okay, and now we have to define what's called the bottleneck distance of the entire clusters, for all the clusters. That I've defined here is, and that's denoted by delta of C, and that's simply the max over all the clusters, max of the bottleneck distance over all the clusters. So that's what I've written here. That's how I've defined delta of C. So essentially delta of C tells you which is the point which is complaining the most, right? So every point complains to some extent, depending on how far it is from its center. So we just want to know which is the point which is complaining the most, right? And the distance of that point from its closest center is called delta of C. Okay. So now what's the goal in k-center clustering? So the objective function is to basically minimize delta of C. Right? We want to minimize the maximum complaint any point can raise. Right? So, I mean, I can think of some applications where this might be important, right? So, say, imagine these centers to be, say, fire stations or hospitals, right? So in that case, we want to ensure that every point in your set P has a nearby fire station, right? Or nearby hospital. You want to take care of all the points, right? You don't want to say that, okay, for majority of the points I'll do well, for some, okay, I can't do much. I'll let them be very far away, right? So this particular k-center clustering ensures that every point is taken into consideration. Even if one point is neglected, its delta of C will be very large, and then that will lead to a large value of your clustering, which you don't want, because here you want to minimize delta of C, right? So the summary is, unlike other objective functions, say k-means, where it's a different objective function, where even if you neglect a few points and if you try to optimize on the remaining points, overall objective function might be pretty small. But here, the way it's defined, even if you neglect one point, it can create havoc. Okay, so what's the goal today? The goal today is actually, again, this is a NP-hard problem. So we'll actually come up with an approximation algorithm, a greedy algorithm, very simple greedy algorithm, which gives a two-factor approximation. So what do we mean by a two-factor approximation? We'll output a set G such that the bottleneck distance for this set G will be delta of G, and it will only be at most 2 times away from the bottleneck distance you will get from the optimal clustering. So there'll be some optimal clustering which we don't know, but that leads to some delta C opt. That will be the bottleneck distance there. And what we will compute will be at most 2 factors away from it. Not bad, right? Okay, so that's the two-factor approximation we are aiming for. Okay, so now it's time to dive into the algorithm. Okay, should we start from the left half or the right half of the algorithm? We'll see. Okay, anyways, the algorithm, the summary of the algorithm is the following. You just bribe the point which is complaining the most, right? So the algorithm consists of k iterations. So let's go through the left half of what's written here. So it just consists of k iterations, and in each iteration, you pick one new cluster center. Very, very simple, right? So after k iterations, you have k center clusters, and you're done. Okay. So how do you start? So in the first iteration, you're allowed to pick an arbitrary point of P. Just pick your favorite point. Okay. So you do that. And after I iterations, you have a set Gi of I centers. Right? That's what is written here. G1, G2, so on of the Gi. So you've collected I centers. Okay. So I think this might be a good time to go to the right half of the screen and look at the example. So what do I mean? So here I'm saying there are n equal to 10 points and k is 3, which means I want to create 3 clusters with 3 centers. So as I said, in the first round, I'll pick an arbitrary center. So I just chose the 3rd point from the left. Okay. So at this point, for everyone, this is the closest center. So we have only one cluster. And which is the point, as I said, the summary of this algorithm is bribe the point complaining the most. Right? So which is the point complaining the most? Right? It's the rightmost point, because in the figure, it kind of looks like this point is the farthest from the center, cluster center. Okay. So then what we do is, in the second round, we make this rightmost point, because it's complaining the most, we make that the center now. Okay, so that's what is shown here in the figure. Now we have two centers, right? And now every point decides, okay, which is my closest center, and appropriately goes there. So that's why we have two circles here, so-called circles, right? And yeah, everyone went to the closest center. And now again, this delta G of 2 that I've written kind of tells you which is the point complaining the most now, right? So that's the point which is farthest from its center. So that is the sixth point here from left. Okay, so then you pick that point as a new cluster, as a new center, and that's the figure you see now. Now you have three, in the figure below, now you have three centers, right? And again, each point decided which is its closest cluster center, and it went there. That's why we have three clusters. Very simple, okay? So let's get back to the left half of the screen. And as I was saying, after I iterations, we have a set Gi of G1, G2 up to Gi, which are the current centers, right? So now we have to pick the next one. So all we have to do is to compute the bottleneck distance, right? So once we do that, let's say P is the point which is complaining the most, which actually led to this delta of Gi, right? So then all we do is we just add that as the next point. So Gi plus 1 will just be this point P, and this capital Gi plus 1, all we'll do is we'll take the set capital Gi and add this new point, small Gi plus 1 into it. Yeah, very simple. Okay, so now the running time of the algorithm. So I'm claiming this can actually run in order of nk time. So to do that, we just need this one variable, small d of p. So we need this variable for every point p in your data set. So initially you can define that to be, initialize it to be infinity, but in general, in every iteration, it basically keeps track of the distance of point P to its closest center, cluster center. So after every iteration, you just execute this formula that I've written there, which is min of its existing distance, which is d of p, and there's a new center which came in, right? Gi plus 1. It just checks if it's better to stay with the current center, or should it choose Gi plus 1 as the new cluster center, right? So it just checks the distance between P and Gi plus 1 and sees which is the better option. It's just a constant time operation, right? So every point does this. So in general, this whole iteration can be executed in order of n time. Right? So that's the main thing. So the rest of the implementation is simple. So in total, the algorithm runs in order of nk time. Okay, so now let's see. So now we are ready to do the analysis. Okay, let's go. Okay, so we didn't talk about which space we are working in. For simplicity, you can just assume we are in the Euclidean space, a two-dimensional nice Euclidean space. But actually, if you look at the analysis carefully later, you'll see that actually it works for any metric space. For people who know what metric space is, right? So only the properties which are specific to metric space will be used. Nothing specific to Euclidean space is going to be used. But for the sake of understanding, you can think of it as an Euclidean space. Okay, so the output of the algorithm finally after k iterations will be this set gk, capital GK, which is the set of which are these G1, G2, so on up to Gk, right? But for the sake of analysis, let's imagine that maybe, let's say the algorithm had run for one more iteration, right? Then it would have output this set called capital G of k plus 1, which would have had one more point in it, which is small g of k plus 1, right? Okay. So we'll work with k plus 1 points, right? So for that, we need this capital G of k plus 1. Okay. So now, if you still remember the definition of delta of gk, which is the bottleneck distance. So when the algorithm terminated, right? So then delta of gk is nothing but the distance between gk plus 1 and its closest center in gk, right? So gk plus 1 was the guy complaining the most, and we're just saying its distance from its closest center is delta of gk. That's the definition of bottleneck distance. Okay, so keep this in mind, delta g of k. It's going to come going forward. Okay, so now we'll make a series of simple observations, 3 observations, and we'll be done. Okay, let's start. Let's start with observation 1. So the first observation I'm making is the following. So I'm saying these delta GIs keep decreasing with every iteration. So recall what delta G of I is. So delta G of I would be that after I iterations, the point which is complaining the most, what is its distance from its closest center, right? So I'm saying these values keep decreasing. And why is that true? It's very simple, because whenever a new center is added, each point's distance is each point either stays with its current center or it chooses the new center, right? Why will it choose a new center? Only if its distance to that new center is closer, right? So with each iteration, every point's distance to its closest center either remains same or it decreases, right? So because the distances are decreasing for every point, actually if you go back to this d of p that was defined before, because it's decreasing for every point, so overall even the delta of GIs will keep decreasing. Okay, and actually let me, even in the figures, if you see, it's not a formal proof, but you can see that the deltas are decreasing over iterations. Okay, so this is important, keep this in mind. And now let's go to the second observation. Okay, so then, so what does this say? This says for any I and j such that I is less than j, let's look at the distance between gi and gj, right? So gi was picked first in the ith iteration. In some other later iteration called jth iteration, gj was picked, right? And now we want to look at the distance between these two. And the claim is it will be at least delta of gk, right? So delta of gk we have already defined here in black, what I've written here, right? So what it's basically saying is, if you look at the distance between any two centers, its distance is at least, so essentially is at least the bottleneck distance after k iterations. So in some sense, the algorithm has done a very good job, because what do we want in clustering? We want that these centers should not be very close to each other, right? They're very close to each other. So then maybe that will not lead to a good clustering intuitively, because there might be points all over your plane. So you want to stretch these as far as possible. Every pair of centers should be as far as possible intuitively. And that's exactly what this observation is saying. It's saying that the distance between any two centers is at least their bottleneck distance, right? So in that sense, every point has found a good shelter. They don't have to complain too much. Okay, so let's prove this. Uh, so let me read out the first line of the proof. So since Gj got added as a center in the jth iteration, that means this point Gj must have complained the most in the j minus 1th iteration, right? That's why it got a chance to be a center in the jth iteration, right? And in that j minus 1th iteration, let's say C of Gj was its closest center, right? In the j minus 1 iteration, it must have chosen somebody as its closest center, right? And after choosing that, it complained the most, right? So that center that it chose, we are calling that C of Gj. Okay. So now in orange, I have written that the bottleneck distance after j minus 1 iterations, which is delta of capital G of j minus 1, is exactly the distance between the point Gj and its closest center, right? It's a simple definition, right? So nothing fancy here. Okay. So now, okay, so then we're done actually. So now if we look at the distance between, therefore, if you look at the distance between Gi and Gj, it has to be at least the distance between Gj and its closest center, right? So if Gi is equal to C of Gj, then it will be inequality. Otherwise, yeah, it will be a inequality, right? So this is an easy inequality to see, right? And then this distance of Gj comma C of Gj is nothing but delta of Gj minus 1. That just follows from the equation written in orange, right? So that's why you get the equality. And now from observation 1, we know that delta of Gj minus 1 is at least delta of Gk, right? That's it, we're done, right? Because these deltas are decreasing over iterations. We have just shown that distance between any two centers is at least delta of Gk, right? Okay, good. Now we are ready to prove the final observation. And now we want to show that this actually leads to a two-factor approximation. Okay. So recall that C-opt is the optimal clustering, and that clustering actually led to a bottleneck distance of delta C-opt. And what is the bottleneck distance that we will be computing, the algorithm will be computing? It's delta of Gk. And we want to show it's two-factor approximation, right? So that's the observation. And it should be observation 3. Okay, I didn't write that, I just said observation. But anyways, okay, let's get started. Okay, so this will be a simple proof by contradiction. So I'll assume that delta of Gk is actually at least 2 times delta of C-opt. Okay, and I'll prove a contradiction. So let's look at the optimal clustering. So this is one thing I really like about approximation algorithms, that we don't know how the optimal clustering looks like. We can't compute it in polynomial time. But somehow we can make use of it in the analysis and show that our algorithm is actually pretty close to the optimum. So it's it's very fascinating in that sense. Anyways, okay, so let's look at C-opt, and let's say C1, C2 up to Ck are the K center points of that optimal clustering, right? C1, C2 up to Ck. Okay, so now by pigeonhole principle, we have K centers here, right, in the optimal clustering. And then I'm saying by pigeonhole principle, at least 2 points in Gk plus 1. So recall Gk plus 1, sorry, recall Gk plus 1, right? It's these K plus 1 points. Okay, so we have K clusters here, cluster centers. And And I'm saying by pigeonhole principle, at least 2 points in this GK plus 1 will belong to the same center in C opt, right? So if you just look at the optimal clustering, right? So then there must be some CL. Let's look at the blue circle here. There must be some center CL such that in its cluster, there must have been at least 2 points of GK plus 1, right? By simple pigeonhole principle, there are K plus 1 points and there are only K center clusters, okay? So some cluster has to have at least 2 points, okay? I should not say this too many times. Okay, so let's say 2 points GI and GJ are in this blue circle, belong to this cluster of CL, okay? If that's the case, then what's the distance between GI and GJ, right? Because we are in the Euclidean space, we can use the triangle inequality, which says that distance between GI and GJ. So I want to connect this to the distance of these points to CL, right? So by simple triangle inequality, distance between GI and GJ will be at most distance between GI and CL plus distance of CL to GJ, right? Very simple. And each of these distances is at most delta C opt, right? Because by definition, no point complains more than delta C opt in the optimal clustering, right? So each of these terms will be delta C opt. So then what does the equation 1 say? It just says that distance between GI and GJ has to be at most 2 times delta C opt, right? Okay. And now from observation 2, let's go back to observation 2. What did it say? It said distance between GI and GJ is at least delta GK, right? Okay, that's what I've written. And what did I assume here? I assume in orange here, I've written that delta of GK is at least 2 times delta C opt, right? Now, as you can see, we have arrived at a contradiction. Equation 1 is saying distance between GI and GJ is at most 2 times delta C opt, whereas equation 2 is saying the distance has to be at least 2 times delta C opt, right? And that's the contradiction. And that essentially shows that this observation here is proven. That delta of GK is actually at most 2 times delta C opt. Okay, so that was very simple, right? Very simple algorithm, very nice set of analysis. We are done. And as you can see, that we didn't use anything specific to Euclidean space here. We just needed properties of a metric space, that the triangle inequality is being satisfied, and the 2 other properties. And anything else I had to say? Yeah, so one question one might have is the analysis type? Well, I leave it as an exercise that you should actually think of an example and a set of bad choices to start with. I mean, the first choice, right, the arbitrance. If you don't start well, then this can actually lead you to close to approximation. Right? You can't avoid 2 approximation. Okay, and would also be a good exercise to think of an example where this doesn't lead to an optimal clustering. But I guess if you try to come up with an example for the 2 approximation, that will also give you an example where this algorithm doesn't give you optimal clustering. Okay, good. So that's all I have to say here. Yeah. So thank you for listening. Bye.